Hi there, this is going to be the last piece for our chapter 17. So we've been talking about the Le Chatelier's principle. Hope everybody remember what is Le Chatelier's principle. So we talk about if you disturb a system at equilibrium, so the system will adjust to compensate the change that has been happened until it re-establish its equilibrium. Okay, so the position will change, reaction will either go forward or reverse reaction. The position of the equilibrium changes, but it does not change the equilibrium constant. Okay, now we're going to look at the effect of change in temperature. So in the last video we talk about the effect of change in concentration, pressure, volume, number of moles. That's it, right? Yeah, so now the effect of a change in temperature. Okay, so determine the effect of a change in the temperature on equilibrium. We're going to consider heat either as a reactant or a product. So basically we're going to treat heat as a component of the system. Now you also need to refresh your mind about what is an exothermic reaction and what is an endothermic reaction. Okay, so heat is a product in exothermic reaction. Remember, if you remember how to write exothermic reaction, let's say A giving you a product B, and then in an exothermic reaction heat is released plus heat, right? Heat is a product in exothermic reaction. Now what would be the sign of the delta H? Heat is the amount of heat, right, released. Now delta H tells us the enthalpy of the reaction, the difference of the energy from the products to the reactants, right? So delta H is going to be a negative value for if it is an exothermic reaction, right? In an endothermic reaction, that A goes to B, meaning heat is a reactant. You have to consider heat as a reactant. You give heat to make A goes to B, so heat is a reactant, and the value for the delta H, the sign for the delta H is positive for an endothermic reaction. Okay, and this is for exothermic reaction. So remember that heat is a product in an exothermic reaction. Delta H is going to be less than 0, negative. Heat is a reactant in endothermic reaction. Delta H is greater than 0, positive. So if you increase the temperature, which one favors that reaction? Where do we find heat as a reactant? So if you increase temperature, it would favor an endothermic reaction, meaning endothermic reaction would take that heat and it will go forward, right? So increase in temperature adds heat, which favors the endothermic reaction. Okay, and then the decrease in temperature, meaning if you remove heat, let's say you are decreasing heat, so you remove heat, what's going to happen? So then the reaction will proceed to the right, making more of the heat that is being lost. So that favors the exothermic reaction. Okay, so remember that. Okay, how does an increase in the temperature affect the equilibrium concentration of the underlying substance and K for each of the following reactions? Now remember, K, equilibrium constant, is going to affect by the temperature. So by changing the temperature, equilibrium constant changes. Okay. Alright, so what we're going to do? How does an increase in temperature affect the equilibrium? So overall we are going to increase the temperature for this system. Calcium oxide plus water, liquid water and solid, giving you calcium hydroxide aqueous, and the delta H naught for this reaction is given as negative 82 kilojoules. So if it is negative 82 kilojoules, is it going to be an exothermic reaction or an endothermic reaction? This is an exothermic reaction. So in an exothermic reaction, where do you find the heat? Is it a reactant or a product? That's going to be a product, right? Because you are releasing heat. So calcium hydroxide plus heat, both are going to be your products. So you increase the temperature. If you increase one of the products, what's going to happen to the reaction? Which direction would it go? Would it make more heat, or would it use up that heat and try to lower the heat that is being added? It would lower, right? So it's going to go making more of the reactants. So which direction it would go? So in an exothermic reaction, if you add heat, it would go to the, if it would shift the equilibrium to the left. Okay, so if the equilibrium shift to the left, what's going to happen? So you have equilibrium constant. Now you are making more of the reactants, right? Remember the Kc term. Kc is going to be products over reactant concentration. Now the equilibrium shift to the left. Left meaning you have more of the reactants, and then you are decreasing the products. What's going to happen to the ratio? Kc going to decrease. Okay, so reaction will proceed to left and the Kc will decrease. Equilibrium constant will decrease. And then what happened to the calcium hydroxide? If the reaction is moving to the left, calcium hydroxide concentration decrease. So it's asking what happened to the underlying substance. So calcium hydroxide concentration will decrease. Kc also decrease. Reaction will go to left. Got it? Okay. All right then. Next one. What happens if you increase the temperature? What effect it would do for the concentration of carbon dioxide, right? Now the delta H is given 178 kilojoules. Now look at the sign of the delta H. Is it exothermic or endothermic? It's positive, meaning it is endothermic reaction. So in endothermic reaction, where do you find your heat? Is it a reactant or a product? Endothermic reaction is it absorb heat. So your heat is a reactant in a endothermic reaction. So heat is a reactant and you increase the temperature. So which direction should the reaction proceed? Left to right or right to left? If you add one of the reactants, it should go to the forward direction to decrease in the added heat. So the equilibrium will shift to making more of the products. So as a result, what's going to happen to the carbon dioxide concentration? It would increase. Carbon dioxide increases. So the product concentration increases, products ratio. So what happened to the equilibrium Kc, equilibrium constant? So Kc will also increase. Okay. And in fact, in the Kc expression, we only can put carbon dioxide since calcium oxide and calcium carbonate is a solid. So Kc will increase, carbon dioxide concentration increase, reaction will proceed, making more of the products, shifting equilibrium to make more of the products. Okay, going from left to right. Now what about the next one? Now again here, what happens if you increase the temperature to sulfur dioxide? Again, delta H note 297. Positive 297. Is it exothermic or endothermic? That's going to be again endothermic reaction. Positive delta H. In endothermic reaction, heat is going to be a reactant heat. Right? Heat is a reactant. So then which direction, if you increase temperature, which direction would the reaction proceed? Since we have added a reactant, then it will proceed to making more of the product. It's going to use up more heat. So then what happened to SO2? Sulfur dioxide will decrease, right? Because if it is moving towards making more of the products, reactant should use up. So sulfur dioxide concentration will decrease. What happened to the Kc? So if the reaction moving forward direction, your product concentrations will increase, right? Reactants will decrease. So as a result, Kc will increase. Okay, and sulfur dioxide decrease, Kc increases. Equilibrium constant. Okay, reaction will go from left to right. Okay, That is also explained here. Okay. Okay, so the temperature and the equilibrium constant. The only factor that affects the value of equilibrium constant for a given equilibrium system is the temperature. Now, the equilibrium constant didn't change by changing the concentration, changing the pressure, volume, number of moles. It doesn't change. Only fact that it affects is the temperature. So, for a reaction with delta H greater than 0, which means endothermic reaction, increase in temperature will cause K to increase. Equilibrium constant will increase because the reaction will proceed making more of the product since it's an endothermic reaction. Okay, for a reaction with delta H naught less than 0, which is an exothermic reaction, if you increase the temperature, it causes K to decrease because the reverse reaction will take place since temperature is a product. Okay, so that relationship is given by this equation. It's called Van Hoff equation. ln K2 over K1 equals negative delta H naught reaction, and this is the delta H of the reaction at two different temperatures, and what are their equilibrium constants. So we can find out that relationship. Okay, K1 and K2 are the equilibrium constants at different temperature 1 and temperature 2. K1 correlates with T1, K2 correlates with T2. Okay. Okay, so that's how the temperature affects the equilibrium constant, and then either the products or the reactants of the system. And then the last one, catalysts and equilibrium. A catalyst speeds up a reaction by lowering its activation energy. We learned about this in the previous chapter. A catalyst therefore speeds up the forward and reverse reaction to the same extent. So, catalyst causes a reaction to reach equilibrium more quickly, but it has no effect on the equilibrium position. Okay, remember that. And then here's a summary. Effects of various disturbances on a system at equilibrium. Now, let's say the disturbance is increase. You increase one of the reactants, excuse me. So the equilibrium position will go making more of the product towards formation of the product. And then is it going to affect the value of the equilibrium constant? No. Okay. You decrease reactant, so then it will go from forming more of the reactants, going from product to reactants. No effect on the K. You increase the product, so then the reverse will happen towards formation of reactants. That's how the equilibrium shifts. Nothing for the value for K. And you decrease the product, so then the forward reaction will take place. No effect for the equilibrium constant. And for the pressure, so increase the pressure. Increasing pressure means decreasing volume. So if the volume decreases, number of moles need to decrease. So the reaction will proceed to the side where you have less number of moles. No effect on the K either. And if you decrease the pressure, meaning increase the volume increases means number of moles will increase. So then it will go toward formation of more moles of gas. It could be the reactant side or the product side. And then the increased pressure, add inert gas. You increase the pressure by adding inert gas, but you don't change the volume. Remember, we talk about inert gas doesn't have any effect on the equilibrium. Nothing will happen, concentration doesn't change, and again no effect on the equilibrium constant. Now with the temperature. Increasing the temperature, if you increase the temperature, reaction will proceed to compensate that increase of the temperature, meaning towards absorption of the heat. Okay, so there are conditions. K can increase if delta H naught reaction greater than 0. The K increases if it's an exothermic reaction. Again, by increasing the temperature, K decreases if it is a exothermic reaction. Okay, this is endothermic, exothermic. Decrease the temperature. If you decrease the temperature, the reaction will proceed towards release of heat. Right? If you remove heat, you are trying to make more heat. So toward release of the heat, again two conditions: increase if depending on the delta H less than 0, meaning if it is an exothermic reaction it would increase, it would decrease if it is a endothermic reaction. Okay, positive, negative. And if you add a catalyst, nothing happened to the equilibrium. Forward and reverse rates increase equally and equilibrium is reached sooner. So there is no effect for the value for equilibrium constant. Okay. Here's an example of synthesis of ammonia. Ammonia synthesized industrially via the Haber process. Nitrogen plus 3 hydrogen giving you 2 ammonia, and this is the delta H reaction. Enthalpy of the reaction is negative 91.8 kilojoules. Is this exothermic or endothermic? It is an exothermic reaction, right? So there are 3 ways to maximize the yield of ammonia. Or how can we make the yield more for ammonia? So this is a gas. 1 mole of nitrogen here, 3 moles of nitrogen. Sorry, 1 mole of nitrogen, 3 moles of hydrogen. So 3 plus 1 is 4. And then you have 2 moles of ammonia. So the number of moles decreases, right? So one way we can achieve this is decrease ammonia by removing ammonia as it forms. So you remove one of the products. So then what happens? As you remove it, the reaction will proceed making more of ammonia. That's one way. And then the next thing is decrease the volume by increasing the pressure. Because we have 4 moles of reactants, 2 moles of ammonia. Right? So you decrease the volume, meaning the reaction will proceed making less number of moles. How do you decrease the volume? By increasing the pressure. So one of these, either decrease the volume or increase the pressure. And then the other one, in terms of temperature, what do we need to do? Now, since this is an exothermic reaction, where do we find the heat? Heat is a product, right? So see, heat is being generated. So you lower the temperature. When you lower the temperature, decrease the temperature, it would proceed to the right direction because you want to generate more heat, the one that is being decreased. So those are the 3 ways that you can increase the synthesis of ammonia. By looking at the equation, we can decide all of these methods make sense, right? And in fact, here's the yield of, here's the Kc, equilibrium constant at different temperatures. You see temperature 200, Kc 7.17 into 10 to the 15. And you can see they are increasing and then the Kc is decreasing. Okay, so lower temperature, it has a higher equilibrium constant and you can have a higher yield. Increase in temperature causes the equilibrium to shift toward the reactants since the reaction is exothermic. Okay, decreases. That's correct. Okay, then that concludes our session on chapter 17.